we can move. Okay. So did I lagged out in between? Hello?
No.
Okay. So I can't open chat. Let's see, where is chat option? Was there something in the chat? Or can we move on to day 2?
You can just ask like if they have any questions, maybe.
Yeah, I am asking that, but I can't see my chat. I don't know why it is not opening. So can you read out the doubt? Okay, guys, if you have any doubts, write in the chat box. And can you, Vamsi, can you read it out? Read it out
I
to
will
me.
read it out, but I think there are no doubts.
Yeah, sure. Yeah, there are no doubts.
Okay, so then we can move on to day 2. So handing over to Sweta, and she would be covering starting with day 2. So Sweta, now to you.
Yeah. So is my screen getting shared?
Yeah, it is name share.
And I'm properly hello.
I think there's some issue with your connection, mic.
Just wait a minute.
Yeah, now it's fine.
Is it fine now?
Yes, yes.
Okay. All right. So let's begin. Welcome back, everyone, to day 2 of PyBullet workshop. My name is Shweta, and I hope you really enjoyed and learned in the last session. And you would have probably read the repository material of day 1 and tried on the basic codes. Even if you haven't, you can reach out to the materials and recording anytime. And for any doubts, even during my session, you can put it up in the chat box or even in the Discord channel if you have any doubts. Okay. So yeah, let's start with today's session. The topic we are going to discuss today is controlling a robot. Since our childhood days, most of us would have been amazed by robots and how are they controlled, and can we also make them work like we want? Well, it's even more fascinating and real, and there's no end to this inquisition. And yesterday also, I saw many of your doubts about how can we bring the robots to motion, and how can we provide velocity, acceleration, and stuffs like that. So today, yes.
Can you please speak a little slow, maybe?
Yeah, sure. Hello. Yeah. So let's start with some basic stuff, sort of a recap from yesterday. Each robot can be assumed to be a tree structure of links connected by joints, as we discussed yesterday. Links give the robot its structure, while joints are used for motion, right? And a simulated robot, as described, as we make it up in a URDF file, has a base and it has links connected by joints. Each joint connects one parent link to a child link. And now, since each link is connected to one parent link and one child link with a single joint, the number of joints is equal to the number of links in any robot we make. Now, one of the primary needs to operate a robot as per our wish is to drive the joints of it. And each joint of a robot, be it a revolute joint or a prismatic joint, as discussed yesterday, is motorized. Like there is a motor attached at every joint, be it in real life or be it just a simulation. And motors, as we know, are machines that induce some form of motion by creating a torque in the case of rotational motors, or force in the case of linear motors or actuators. Now, had we been dealing with hardware stuffs, then the design of motor and its specifications would have been required. But since here we are dealing with simulation, so the motors are driven by physics engine. So we would be focusing on the physical properties of the motor and just see a demonstration of how would it work in real life. Like its closest approximation, you can say. Like if we are building a bot and we attributed some functions, say it has to go from one corner of the room to another and pick up an object kept there. So in simulation, we can just place all of the things together and check if it's operating properly or not. If there are any errors, then we can rectify it then and there instead of making the entire hardware stuff and then discarding it, right? So yeah, our motor in simulation would be driven by pi bullet physics engine. So how are we going to control the joints? So we have a pi bullet function to our rescue over here, which is set joint motor control function. Set joint motor control 2 is an import function which allows us to control a robot by setting a desired control mode for one or more joint motors. It controls the motors in a robot by providing the desired velocity or maybe position or torque. Now, during the simulation, the physics engine will simulate the motors to reach the given target value that can be reached within the maximum motor forces. Now, while writing the function, the set joint motor control function, you would need to provide some input parameters for it to work, right? So these are the input parameters for set joint motor control function, which basically include the body unique ID. This is the ID returned from the load URDF function, which signifies the robot body. Like yesterday, we had used the p.load URDF function to load any bot, like for the 2R arm as well. So the ID, which is returned from the load URDF function, that signifies the robot body we are working on. Like it's a kind of code name for your bot in pi bullet. So this will be feeded in first. Next, we have joint index, which corresponds to the joint we are working for. Like suppose we are working on a manipulator arm, which has 3 links and 3 joints, and we want to move the wrist part of it. Then we need to feed in the wrist joint ID. And how are we going to get that particular ID? That I'll show you further. Next, we have 3 control modes, which are going to be position control mode, velocity control mode, and torque control mode. I'll be explaining them one by one further. And then is the target position, which is used in position control mode, target velocity in in velocity control mode, and then is the force. I'll explain it further. Yeah, so as I said, how are we going to know which ID corresponds to the wrist joint ID? So we'll use get joint info function for it. Now, according to whatever task we have, we need to move different joints in different manners. Also, not all joints are used for motion, right? So we need to have information of all the joints we are having. And for each joint, we can query some information such as its name or its type or its index, etc. So get joint info will again be taken 2 input parameters, namely body unique ID and the joint index. Like suppose we have one joint in our system, then we obviously know that the index of this joint is going to be 0. Say we have 2 joints, then they'll be numbered 0 and 1. But if we are having a multi-joint system, which is true for most of the cases, then for knowing the number of joints in our system, we can use getNumJoints function, which would return an integer that corresponds to the number of joints in that body. Let's just understand it by taking an example of a car. So here, what we have done is basically we have imported pi bullet, then we have loaded a simple car. This is the URDF file of the simple car. We have loaded it with the function p.load URDF, and the body unique ID of the car is stored here in this word in car. So further in the code, wherever will be needed to put in input of body unique ID of the bot we are using, then we'll be using this word car. Now we have created a variable number of joints, and in that we have used the function p.getNumJoints, as I said. it takes the input of just the bot we are using, which is car in this case. So what it does is it just counts the number of joints in the bot, and it gets stored in this variable, which is number of joints. So suppose our car has 5 joints. Say our car has 5 joints. So number of joints now becomes 5. Now we created a loop. What this loop basically does is it iterates a number of joints times. So if we are having 5 joints, it will iterate from 0 to 4, which means 0, 1, 2, 3, and 4, right? So this loop will go on 5 times, and each time it's going to take the info, which is calculated from p.getJointInfo. Now, as discussed, it is taking 2 input parameters, which is the body unique ID and the joint number, which will go from 0 to 4, and it will print the information. So let's try to use it on a Husky, so you'll understand it better then. Yeah, so firstly I've imported the basic imports, then I've loaded the plane, and then I've loaded the Husky. See, this is the Husky. I've used the p.loadURDF function. I've loaded the Husky, and this is the position I want my Husky to be at, the initial position. So this 2, 0, minus, 0.1 is the position I want my Husky to be loaded at. So then I need to know what are the number of joints in my Husky, the total number of joints. So the piece of code I'll be implementing is this. NumJoints is equal to, NumJoints is the variable I've created, is equals to p.getNumJoints, and the input parameter it's taking is just the body unique ID, which is Husky in our case. Okay, so it'll print the number of joints. Let's just print it. Yeah, so here it's printed 10. So this basically means that the number of joints present in our Husky is 10. But now how do we know? Suppose we need to perform some control over the wheels of the Husky. So how do we know that which joint ID corresponds to the axle of the wheels of the Husky? So for that, I'll be using the getJointInfo function. I've created a loop in the similar way as that car example. So it is going from 0 to 9 this time, since NumJoints is 10 in our case this time. Yep, so we have used the getJointInfo function. The input parameters are the body unique ID, Husky, and the joint number, right? So let's run it. So here we can see a list of information about all the joints is printed. See, from 0 to 9, all the joints and the information related to all the joints is printed. So the joint IDs from 0 to 9, the joint name as it was specified in the, it would have been specified in the URDF file, then the joint type and a bunch of other information. So everything is printed over here. Now, from this information, we can figure out that the front left wheel corresponds to the joint ID 2. The front right wheel corresponds to 3, rear left wheel 4, rear right wheel 5. So now we know that whatever control we are going to perform is over these 4 joints, 2, 3, 4, and 5 for the axles of the wheel. So this is how we can get the information related to the joints in a bot. Okay. Now let's move ahead. Yeah, after we are getting the info, the joint IDs, then these joint IDs along with the Husky ID would now be passed on to setJointMotorControl function, wherein we'll regulate the motion of these joints to either control the velocity or the position of them. Okay, so next we have control modes. Like here we discussed the third parameter over here is control mode. So there are 3 control modes. So what is a control mode? Every motor in pi bullet is characterized by the maximum velocity and maximum force it can exert. Every joint by default has a motor, as I told you, attached to it. And hence, we just need to give the motor's desired position or velocity or torque to control them. So there are three control modes: position control mode, velocity control mode, and torque control mode. So let's take position control mode first. Position control mode implements the most basic way to control a joint. Like, we can specify the position we want a particular joint to be at. And in accordance to the position given, velocity is calculated for that joint. Like, the difference is calculated between the actual position of the bot and the desired position of the bot, and accordingly the velocity is calculated for that joint. In position mode, user can set limits to torque and velocity as well. Like, if we want our motor to work only within a certain torque limit, then we need to specify that, and the motor will work between that specified limit, minus tau and plus tau only. Now here, the target position could be in meters if we are dealing with joints like prismatic joint, which just performs motion in one degree, like it translates. So there we have to give the target position in meters. Also, it can be in angular position, it can be in radians if we are dealing with a revolute joint, right? So it's pretty obvious. Now these are some applications of position control. It be pick and place machines, 2D, 3D print, welding, etc. Yeah, so this is basically a snippet which shows the syntax of how can we implement position control mode. So we have used the set joint motor control function, we've used the first bracket, and then these are the input parameters, as I discussed, the sequence of the parameters. The sequence of the parameters is very important. We cannot juggle the mess up with the arguments. Like, we cannot put the control mode first and then the body index. The sequence is very important. The first input parameter needs to be the body index, body unique ID. Then second is the joint index, for which I want to control the position. So I've specified the control mode to position control mode. Then I've given the target position to be POS in this case, and the force with which I want the motor to be driven with. So it's maximum force, and whatever the maximum force you want to specify. So let's just understand it better with the help of a 2R robot arm. Like, you are familiar with 2R robot arm. So let's just recap what is basically a 2R robot arm. It has two links and it has two joints. The two joints are of revolute joint type. Okay, so let's draw an analogy between a human arm and a 2R robot arm. So we have the first link and the second link, which are the two limbs in our case. And then we have the two joints. The first joint, which is the elbow joint, and the second joint, which is the one connected to the shoulder. So in this case, the joint ID 0 corresponds to the shoulder joint, and the joint ID 1 corresponds to the elbow joint. So firstly, I've simply loaded the robot arm. This is the URDF file of the robot arm. I've loaded the plane. I've set the position and orientation. Simply the gravity is set to 0 in my case. You can even define it. Then I've used set joint motor control function twice. Why twice? Since we are having two joints, I've used it twice, once for the shoulder joint and once for the elbow joint. And see, I've used the proper sequence of the input parameters. First is the body unique ID, which is robot in this case. It's stored in robot, right? Then I have the joint index, which is set to 0 for the shoulder joint. Then we have control mode specified to position control mode, and the target position is set to 0 radians for now. For now, I've set it to 0 radians. It's a revolute joint, right? So it will be in radians. And the force with which the pi bullet is going to drive the motor and move the robot arm to that particular position is 100 Newton. So you can change it accordingly. Now, this for the second time, all of the things are same. Just we have used the joint index to be 1. Let's see first. Is my screen getting shared?
We can just see your code, not the whole screen.
Wait a minute. Yeah. Is it visible now?
Can you try switching the screen? Yes.
Yeah, so this is our robot arm, and as expected, it's standing. It's not bent at any angle. This is the joint index. This is a joint ID with index 0, and this is the joint ID with index 1. So it's bent at 0 radians right now. Okay, so let's specify some angle to it. Suppose I am giving 0.5 radians to it, and I try to run it. See, this joint is bent at an angle of 0.5 radians. Now, if I want to give some angle to this joint as well, you can do that too. So I just need to specify it over here. Yeah. So this joint is now bent at an angle of 0.8 radians, and this joint is bent at an angle of 0.5 in relation to this link. Like if I extend this link in this direction, then this angle is going to be 0.5 radian. So in a way, we can say that this link is bent at an angle of 0.5 plus 0.8, 1.3 radians angle with the z-axis. Okay, so whatever the angle I'm going to be providing for this joint, it will be in relation to this link. So this was about position control. You can perform it on mobile robots as well. I've shown it a simple case for a 2-hour robot arm. Let's move ahead. We have the velocity control mode. Now, by default, each revolute joint and a prismatic joint is motorized using a velocity motor. Here in this mode, we feed in the desired velocity. Goal of a velocity control is to regulate the motor speed. That is, if the user sets the velocity to be 500 RPM, then the motor attempts to rotate exactly at 500 RPM, no matter how much load is attached to the motor. This velocity could be a linear velocity, like in meter per second, if we are using a prismatic joint, or it can be angular velocity if we are dealing with a revolute joint. So it depends on the type of joint we are using. Like for a fan motor, we cannot provide velocity to be 50 meter per second, right? It needs to be in RPM. So yeah. Now, in velocity control mode, user can set limits for torque as well, but not for position. Now, when that maximum torque or force which we are providing is very high, then the target velocity is reached instantaneously, and the joint operates in velocity control mode. Otherwise, if it's not high enough, then it operates at the specified torque or force until the desired or target velocity is reached. And this is the implementation, sort of the syntax. How can we use? So similarly, like the previous one, we have used the set joint motor control function. The input parameters are body unique ID, the joint index. The control mode is now specified to p dot velocity control. And this time we'll be specifying the target velocity, which is VEL in this case, velocity. Whatever velocity you need to be providing, you can feed in that. Then is the force, whatever force you want the motor to be driven with, like limit. Okay, so you can be putting in that. So let's try to perform velocity control over our Husky. Let's go back to our Husky. Yeah, so here this time we know that the joints over which I need to perform velocity control is 2, 3, 4, and 5, which we found out earlier. So let's first define what velocity I'm going to be giving it in. So the target velocity is -5, and you can accordingly change it according to your wish. Okay, so and the maximum force is 100. Now let's create a loop which goes from 2 to 5, and what it does is it just uses the set joint motor control function 4 times. Again, it's taking the body unique ID, the joint index, which will go from 2, 3, 4, and 5, and it's using the velocity control mode. Then we have specified the target velocity, which is -5 in this case, and the maximum force, which is 100. Okay, so we'll try to run it. Is the screen like paused for you all?
No, means the bolt is moving.
Just wait. I think there's some technical issue. That's why it's not moving regularly. Yeah, so basically the point was that we need to just specify the velocity. Whatever velocity we are specifying, the set joint motor control is just putting in that velocity to those specified joints. Now for the first few simulations, I used velocity to be -20 radians per second. Now if I want to reverse the direction for the next few simulation steps, I'll just use this piece of code. I've used the same code over the same loop over here. This time the target velocity is going to be 20, the opposite of -20, right? So let's run it. Yeah, so for the first few simulation steps, it's going ahead. And for the next few, it will come back. Like this. So this was a simple example of performing velocity control over the wheels of a Husky. Next, we have the torque control mode. So torque control mode makes the motor a force or a torque transducer. That is, user sets torque, whatever torque the user wants to set. Like if the torque is specified to be 1 Newton meter, then the motor will produce 1 Newton meter torque regardless of the spinning speed. In torque mode, user cannot set limits for velocity or position. It's pre-calculated. You cannot provide any limits for that. Now, this torque is applied at each simulation step. And since by default, each revolute joint and a prismatic joint is motorized using a velocity motor, we can disable those default motors by using a maximum force of 0. So what's going to happen, even if we are using velocity control mode and we need to perform torque control over it, then we can specify the force to be 0. Nevertheless, we can discard it. Firstly, let's see how to perform torque control. These are the applications you can see. Next, we have the implementation of it. So similarly, the loop we have used the set joint motor control function. We have given in the input of body unique ID, then the joint index. The control mode is specified to torque control, and whatever torque you want to give in, you can give it over here. Yeah. Set joint motor control array. So in most of the cases we'll be dealing with, we'll have multi-joint system, right? So this function enables us to manipulate multiple joints together. That is, instead of giving in one joint at a time, one joint index at a time, here we'll give a list of joint indices. So set joint motor control array function, it will manipulate all the joints together. All the rest of the parameters would remain same. And also target position and target velocity, which we gave, that will also be a list of values. Okay, so it will be a list of float values. So this function will reduce the calling overhead for us. It will manipulate multiple joints at a time. Now, since we have set the joints and links in motion, and there are a handful of other functions too, which could help us to get the information about a particular joint or link during any step of simulation. So these functions are get joint state and get link state. So get joint state is a function which would enable us to get information about a joint, and it returns a variety of arguments. Like it would return us the joint position, joint velocity, reaction forces, and what are the input parameters it would take. It's going to take the body unique ID and the joint index, like we used it in the get joint info. Similarly, here also we'll be giving two input parameters, that is the body unique ID and the joint index. And the output parameters are going to be the joint position, the joint velocity. Position is going to be in the world frame coordinates, Cartesian coordinates. Okay, then we have the joint velocity, reaction forces acting on that joint, and the motor torque. So what is this motor torque? If we had applied say velocity control mode or position control mode to our joints, then the torque applied to the joint motor during the last simulation step will be returned. And if we had used the torque control mode, that is, we have specified the torque which is going to be acting on the joint at each simulation step, then it's obviously going to return the same torque which we had applied. Okay. Then if we use get joint states with the S, then this is the same as get joint state only. It's just that it will return the information about multiple joints at a time. So we need to give the input of multiple joint indices. It will be a list of joint indices. Now we have get link state function. So as the name suggests, get link state returns a bunch of information about a particular link in Cartesian world coordinates. The input parameters are the body unique ID and the link index again. And it returns the position of center of mass of the link, the orientation of the link, the inertial frame position, and a bunch of other arguments too. So it basically returns all of the information about a link at any particular simulation step we want. And get link state with a S will return the information for multiple links. Instead of link index, it will accept link indices as a list of int. So this can improve the performance by reducing calling overhead for each link explicitly. So moving on. Next, we have constraints. Now, so what are constraints? I mean, what is the basic meaning of it? It's some form of restriction to our motion, right? So like, think it in this way. There's a cow which was free to move in a wide ground, but now you have tied it with a rope to one corner of the field. So now it can only move a certain amount of area. and its motion is now subject to the anchor it is linked with, along with the type of rope we have attached it to. We can say constraints limit the movement of two rigid bodies in relation to each other, or the movement of one body in relation to the global world space. Like in the case of cow, we linked it to the global world space. We linked it to the ground itself. We anchored it to the ground. So its motion, despite of being completely free to move anywhere around the field, now it's able to sweep just a small area of it. So its motion is now subject to the type of rope it's connected with, like the type of constraint it's connected with, and the anchor. Okay, all right. So we create bodies as tree structures without loops, and creating constraints allows us to connect specific links of bodies to close those loops. Like motion of the bodies after creating a constraint would take place relative to each other, as if they were joined in by some joint. So we can also add a constraint between a body and a point in the world, like adding a constraint between a single body and a fixed point in the global world is similar to adding a constraint between two rigid bodies. The difference is that you only pass one body and one frame to the constructor of the constraint. So the question arises that are constraints like joints? So, well, we can assume them to be abstract joints. In fact, another often common used term for constraints is joints. Here we can see different types of joints which are analogous to the joint types we have discussed about earlier. All of them serve different purposes and work uniquely, be it a fixed constraint, a point-to-point type constraint, or a prismatic constraint, or a Gare constraint, anything. Okay. So create constraint is the pi bullet function, which in this case helps us to create a constraint. The input parameters. Okay, so the let's try to figure out the input parameters. We are creating a constraint between two bodies, right? So obviously we need to give the body unique ID of both the bodies. So we need to give in the parent body unique ID and the child body unique ID. These two are obvious. Then for both the bodies, we cannot like connect both of the bodies entirely. We are going to connect one link of the first body with certain link of the second body, right? So we need to specify which link are we going to connect. Like if we are connecting link 1 of body 1 to link 3 of body 2, then we need to feed in those indices also. So we have the parent link index and the child link index as well. And remember the sequence with which we are writing these. Then we have the joint type. The joint type, which means like these fixed constraint, point-to-point constraint, prismatic constraint. So we need to specify the joint type. Then we have the joint axis, which is going to be a list of 3 floats. It's going to be a 3-dimensional vector. Okay, so this will be the axis about which our joint is going to perform, about which our joint is going to work. Then we have the parent frame position. So parent frame position is the position of the parent of the joint frame relative to the center of mass of the parent body. I'll repeat it again. It is the position of joint frame relative to the parent center of mass frame. It will again be a list of 3 floats. Then we have the child frame position, which is again the position of the joint with respect to the child's center of mass, child body center of mass. So I'll explain it by a code and it'll be better understood. Let's try to code it up and see different types of constraints.
Maybe Sneha, you can once ask that if they're following with you, because it has been time. So
Yeah. So is anyone having any doubt by now? I mean, everything is your understanding, right? I'm not able to see the chat box, maybe.
maybe if even if you're able to understand everything, you can drop a yes in the chat box. Yeah, you can continue, Sneha.
Okay. So over here, firstly, I've done the basic imports. Then I've imported, then I've loaded the plane. And this time I've loaded 2 cubes. Both of them are same cube. See, you can see the URDF file for both of the cubes is same. This and this. But the position over which I'm loading it is different. For the first cube, I'm loading it on 0, 0, 1. And for the second one, I'm loading it on 1, 0, 1. And the body unique IDs for both of them is for one is cube ID 1 and for the second is cube ID 2. So the body unique IDs is saved in both of them, and I've set the gravity to be 0, 0, 0. I have not set any gravity right now. So then I've created the simulation loop, which is an infinite loop in this case. So let's just run this first. Yeah, so here we have not created any constraint between the cube or the environment or between the 2 cubes. We have not created any constraint, so it will be completely free to move. We can see it's completely free to move. Since I've not given any gravity, so it's not falling down also. So it's free to move. It's floating everywhere. Both of them are completely free to move. Now let's create a constraint between them. Like let's create a constraint between the first cube and the world frame. So this is the line I'll be using. So I've used the create constraint function, p.create constraint, and the input parameters, as we discussed, are going to be the parent body unique ID, which is cube ID 1 in this case. And I'm going to create a constraint between the cube and the world frame. So for the world frame, the index is going to be -1. Whenever you are creating a constraint between a body and a world frame, then for the world frame, you're going to be using the ID -1. So that's why I've used -1 over here. Now for the links, the parent link ID and the body link ID. The parent, for the parent, which is cube ID 1, I'm connecting the base. It's only having one base, okay? It's only having one link, obviously. So I'm giving over here the link index to be -1. Then for the parent link index, it's -1 since we are dealing with the world frame only. So there are no links as such. Then the joint type is going to be fixed type. Then we have the axis, which is 0, 0, 0 in this case. Then by simple geometry, you can figure it out where you need to put the joint. Like in this case, I've set the position of joint. This parameter is the position of joint with respect to the parent body, which means what position of joint I feel to provide with respect to cube ID 1. The position of cube ID 1 is 0, 0, 1. So this is the reference now, 0, 0, 1. And with that reference, what is the joint position I want to be providing, or the constraint position which I need to be providing. So this is 0, 0, 0, which means basically I've created a joint at this position only, 0, 0, 1, which is the center of mass of cube 1. So I've created a constraint between the first cube and the world frame, and the joint position is set to be at the center of mass of cube ID 1. Okay, and this is the position of joint with respect to the world frame, which is 0, 0, 1. So this is the simple geometry. You'll understand it once you try to implement it on your own. Yeah. So this time, this cube, second cube, is free to move since I've not created any constraint. Okay, but this cube is connected to the world frame with a fixed type of link. So see, it's not moving at all. It's fixed over here. So this is what constraint does. This is what a fixed constraint does basically. Now let's change the constraint type to a point-to-point type constraint. So I'm creating a point-to-point type constraint between cube 1 and the environment. So all of the parameters are the same. Cube ID 1 is the parent body unique ID. Then I have the child body unique ID, which is -1 for the world frame. Then I'm connecting the base of it. So -1 is the parent link index and -1 for the world frame index. Now the type joint type is said to be point to point. Now let's run it. This time also the second cube is free. I've not created any constraint, but the first cube is constrained to the environment with a point to point type constraint. So see, it's freely rotating about its center of mass. Why about its center of mass? Because we have created a constraint at the center of mass. Okay, so it's rotating about a single point. So it's fixed to the environment with a point-to-point type constraint. Now let's try to create a constraint between both of these cubes. So this time the parent body unique ID is going to be cube ID 1 and the child body index is going to be cube ID 2. Okay. And since for both of the cases, I'm connecting the bases of them, I'll be feeding in the parent link index to be -1 and the child link index to be -1 again. This time also, this time the joint is going to be fixed. So what I'm doing is I have created a constraint between the first cube and the environment of the type point to point, and I've created a constraint between both of the cubes, which is of the type fixed. Let's see how it works. This is now this time connected. It's not moving anywhere.
Shweta, could you just look into the chat? There's a question for you.
Vamsi, can you repeat what you said?
Yeah, I need to go back to over there. Wait a minute. So what happens if you do to the fixed constraint but swap the parent and the child shown in the example shown previously? So it will work in the similar manner, like what happens is whatever movement I'll be giving to the parent. Hello. So whatever movement I'm going to be given to the parent body, the child body is going to be moving in a similar manner. It'll kind of follow the parent body. So this is the meaning of specifying which is going to be the parent body and which is going to be the child body. The child body follows the motion of the parent body. And so let's continue. Is there any other question? Yeah, so this time I've created a fixed constraint between both of the cubes, and the first cube and the environment is connected with a point-to-point type joint. So we can see that the first cube is again moving about its center of mass, but this joint, this second cube is now also moving along with it. Yeah. See, both of the cubes are not separating at all since we have connected it with a fixed type of joint. Now let's do one thing. Let's create a constraint between the first cube and the environment of the type fixed. But this time, let's create a constraint between the first cube and the second cube of the type point to point. Okay. So our first cube will be connected to the environment with a fixed constraint, while the first and the second cube are going to be connected with a point to point type constraint. See, this cube is fixed, it's not moving, but this cube, see, this cube is moving about a single point. I've specified the joint to be at this point, right? At this point. That's why it's revolving about this single point, while the first cube is just fixed at its place since I've connected it with a fixed constraint. This cube is moving about a single point. It's revolving about a single point. So this is what point to point type constraint basically does. Next, let's do one thing. Let's try out prismatic constraint. So what a prismatic joint basically does is it translates in one axis, right? It's free to move about one axis. It can translate in one direction. So similarly, the prismatic constraint is going to do the same. It can translate in one direction. Okay, so I've created a constraint between cube 1 and the environment of the type point to point, and I've connected both of the cubes with a prismatic type constraint. So let's see how it works now. The first cube will be revolving. See, the first cube is fixed at its point and it's rotating about its center of mass, while the second cube is free to move in one axis. See, it's translating. The distance between both of the cubes is increasing steadily. However, both of the cubes will rotate in the same manner. See, both of the cubes are rotating in the same manner, but the distance between them can increase since it's a prismatic type of constraint.
Sweta, sorry to interrupt. Like, could you check the chat once? I think someone has a question.
Okay. Can they move around, but the constraint is the distance between them in a range? I didn't understand this question. Would you please elaborate? Okay, so it depends on the type of constraint. Like if we are providing making a fixed constraint, so they cannot move far from each other. Both of the cubes cannot move. They are stuck at one place. But if we are using a prismatic type constraint, they can move far from each other, since a prismatic type constraint can move about one axis, right? So it can translate about one direction. So the distance between them can increase. Similarly, if we have a point-to-point type constraint, so it's not moving anywhere further, it's just rotating about a single point, and that what is going to be that point, we are going to define that coordinate. Like whatever we provide the constraint position, the cubes or the bots are going to the link is going to rotate around that point only. I hope I answered your question. Is it possible to add a velocity of torque to a constraint we have created? I don't think so. A velocity to a torque. No, I don't think we can give a velocity to a constraint. Yeah. What is joint axis? Joint axis is the axis about which we want our joint to be working. Like if I'm creating a prismatic type constraint, okay, and I want the cube to be translating in one axis, so I need to provide that axis about which axis I want the translation of that particular constraint. So that's going to be the joint axis. Similarly, for point-to-point type constraint, if I'm providing an axis, it's going to be revolving around that axis only. So this was about the axis. Okay, any more questions?
Yeah, 1 minute, Sweta. Before you proceed, am I audible, by the way?
Yes.
Yes.
Yeah, so only one thing I'd like to add on to the question here. Can they move around, but the constraint is the distance between them is a range. So I'm just hoping that the person is asking that, whether, let's say there are two objects constrained somehow or the other, but the constraint actually is the distance between them, and they can move within that distance, but not more than that. So if that is the case, just to elaborate, like as Shweta mentioned, so you'll in point to point when you define the joint frame, right? So the joint frame can be anywhere in between the two objects, right? So essentially it's nothing but the distance from the child frame to joint frame plus joint frame to parent frame. So that is the maximum distance. So essentially when you have a point to point constraint, the objects are allowed to go within that distance anywhere, but they cannot move away from each other more than that distance, the summation of the two lengths, right? So if that is what you mean by the distance between them is a range, then yeah, you can limit them by an upper bound, but not a lower bound. I think, yeah, not exactly a lower bound. Yeah, I hope that makes sense. Yeah, Shweta, you can continue. If you have anything to add on, you can, but yeah, if not, you can continue.
Okay. Yeah, so I think I showed the prismatic type constraint also. Okay, so yeah, so in every type of constraint we created, in all the cases, create constraint function will return a unique ID in the form of an integer that can be used to change or remove a constraint, okay, or query some information about a particular constraint. So we have a bunch of functions for that, like wait, I'll show you. So these are the functions. Whenever we create a constraint, a unique ID of that constraint will be returned to us in an integer form. And using that unique ID, we can perform these many functions. So say we have created a constraint and we want to change any particular property of that constraint, like we want to change the axis of it, or we want to change the position of that constraint. So what we can do is we can use the change constraint function. It allows us to change any parameter of that constraint, and what input it takes is the constraint unique ID. Get constraint unique ID function, it simply fetches the unique ID of the constraint being queried. Okay. Then we have get constraint state function. It is similar to get join state function. It just brings all the information related to that particular constraint at any particular step of simulation. So it takes the input of constraint unique ID and it brings back all the information related to that constraint. Then finally we have remove constraint function. It will remove a constraint given by its unique ID. Okay, so these were the functions we could be using. And you can put any other questions also if you have in the chat. That was all from my side. I'll be handing it over to Arjun. If you have any questions, you can put it in the chat box. I'll be answering meanwhile.
Yeah, maybe we can take a 5-minute rest
Yeah.
before Arjun begins.
Okay.
Yeah, in this 5 minutes gap, I guess it was very well explained. But one more way to just, a better understanding of constraints, or just to imagine them, better way would be, so let's say you take a fixed constraint. So, and you have two objects. So it means that you're just connecting the two objects with a fixed rod, like there is no motion at all with respect to each other. And let's say you have a point-to-point constraint, then that means that you're connecting two objects with an inextensible rope. So there is an upper bound in the distance between them, but not essentially a lower bound. So they are allowed to rotate or do whatever they want, right? So it's like a extensible rope. And finally, in prismatic joint or prismatic constraint, it's going to be nothing but a rail. So like a rail system. So in a single dimension, you're allowed to move. That's about it. Right. So this is just a better way to imagine constraints and understand. Just wanted to add on.
Yeah, I guess we can start now. Arjun?
Yeah, sure. Is the screen sharing disabled as of now?
You
Can you
cannot
try now?
share the screen. What?
Can you try sharing now?
Yeah, it's working. Right. So is my screen visible?
Yeah, it is.
Hello?
Yes, you're visible. Yeah, your screen is visible.
Okay. So welcome back, right? Uh, my name is Arjun, and I'll be taking over for the rest of the day, right? And as you can see, we'll be going through. This is what the next topic, right? The kinematics, robot kinematics. And so this is one of the very fundamental parts of your further journey into robotics. So even if you like, if you take a undergraduate program or maybe postgraduate program in robotics, this is one of the main things that you will learn. What is kinematics and how do you apply it to robots? So as you can see, I like to describe it like it's all about taking control, right? So in the previous section, Shweta is section, you saw a lot of ways, right? You saw a lot of ways that you can control your robot. You have different methods. You have position control, you have velocity control, you have different constraints. So you learned all of that. You learned the functions and what they do, how they work, and how can you use them. Now, this is actually about taking control. This is like how do we actually apply them in, and just not randomly, but in a more systematic way or in a more planned sort of way, right? You can say in a scientific way. So we'll be discussing how to move robots the way we want by our ways. Maybe in some trajectories. We'll be going over some trajectory planning, motion planning. How does that work? What is the math and science behind it, and all of that. All right. So let's get started. So, is there any? Okay. Okay. All right. So let's move on. So the big question, right? So what is kinematics? I'm sure this is a very familiar term, right, guys? High school memories or nightmares for that matter. So it's a very familiar term, right? I guess you have all heard about it. And this is it, right? So kinematics is just a fancy way to describe motion. So it's just a fancy word for motion. It's all about motion, describes motion, and somewhat like that, right? So to be more specific, it's actually the study of motion. So we analyze, we study like how the position changes, how the velocity changes, how is the motion affecting. So that is all what we study in kinematics. So yes, so as I mentioned, it is a study, it's an analysis of motion. And what exactly are those things? There are variables that we are looking at, right? So one of them is position, very well known, very famous. And another one is velocity. So in this, what we're actually trying to look is how does this apply to robots? Like how is position important for us in robotics? How is velocity important for us in robotics? So we all know for rigid bodies, right? We have studied that in physics with ropes and pulleys and other stuff. That is not what we're looking right. we're looking into how we can apply them into robots. How can we move them? How can we, set the trajectory? How can you specify the speeds and everything? So this is what we're going to be going over today. And there are other two things that you might also have learned, which is acceleration and forces and torques. So about these two, they are important, right? It is important to know the forces that are acting on a robot, like how much the robot can lift a weight or how much can it take up a load, right? But since we're running on a simulation, our robots are essentially super strength, right? Infinite forces can act and nothing is going to happen. We don't really care about forces and torques and acceleration in simulation, right? Because we're working simulation anyway, so we really don't care about these two things. So these two things are what are causing the motion, right? Acceleration, forces and torques are causing the motion, and position and velocity are the two things that is describing the motion essentially, right? That is what we see in front of our eyes. So we will basically from now on look at position and velocity, and we'll ignore acceleration and torques for now. All right. So moving ahead. Right. So I don't know how many of you feel very droozy right now, right? This is all physics 101 all over again. So why am I learning? Why am I stuck here? So like this, it's a very popular internet debate. It's a very firing debate, and you really can't argue with Sheldon over here. That it's a very heated fight between physics and engineering. Is it important, or who is best, and all of that. So unlike what this is portrayed in a lot of sitcoms, physics and engineering, usually always go hand in hand, right? So if you have any sort of research development team, they're trying to solve a problem, you'll always have a panel of physicists, you'll always have a panel of engineers, right? So you'll have both of them working together. So that is what is usually happening in real world. And so this section contains a little bit of physics, a little bit of maths, right? And it's not boring, but so if you better understand the physics, the workings behind the math behind it, you'll be better as an engineer, right? You know what you can exploit, what laws can you exploit. So you'll be a better engineer if you know the principles of physics and maths that works behind any sort of engineering workpiece. Okay, so keeping that in mind, we'll continue. So let's move ahead. So right. So in kinematics, specifically in robot kinematics, there are some questions that we're actually looking answers to, right? And these are the questions of major concern. So there are specifically two questions, right? And the first question, all right, let's get into it. Let's not waste any time. So this is my first question, right? So given a set of joint variables, what's the position of end effector of my robot? I want you guys to answer something. How many of you understand these highlighted terms? Joint variables, end effector, yes, no, somewhat. Guys, you know what this, or should I briefly go over? No, don't know. Okay. All right. So I thought some of you might know. That's why I highlighted. Okay. So I'll just quickly go over them. Right. What they are, what they mean. So joint variables are, you already learned that your robot is made up of joints. Okay. That is very well set as of now. Your robot is made up of joints, multiple joints. And the joint variables are the variables that describe each of the joint and the configuration of each of those joints. So I'll take a very relatable example. So just look at your arm, all right? So if you look at your arm, left or right, whatever it is, you will have three joints, right? You have one over your wrist, and you have one over your elbow, and then one over your shoulder, right? And this is very similar to a robot, and sometimes we also make biological robotic arms, and so this is a very similar thing. So your arm is made up of three joints. One is there at the wrist, one is there at the elbow, one is there at the shoulder. So there are three joints. What are the joint variables? So let's say I rotate my wrist like in maybe 30 degrees upwards. I rotate my elbow maybe 90 degrees upwards. and then I also rotate my shoulder by some angle. So these angles, right? These angles that describe the configuration of our joints, they are called joint variables. So I could say that my wrist angle is alpha, my elbow angle is beta, my shoulder angle is gamma. So if I give some alpha, beta, gamma, then my hand will be in some configuration. It will be in some position, right? So does that make sense? Do you guys need a further explanation on that? Yes. Okay. Cool. Cool. Right. So that is it. Right. So those are joint variables. Joint variables basically describe joints in what configuration, what position are they in. So if it's a revolute joint, it will be an angle. If it's a prismatic joint, it will be a distance. So depending upon the joint, it will have some variable of some unit. It could be angle, it could be distance, it could be anything, depending upon the joint, right? The end effector. The end effector is essentially the final tooltip. So if you have a robotic arm, at the end of the arm, you will have a tooltip, something to grab, something to, pick, or it's like something like finger. So essentially, if I rephrase this whole question, what I'm trying to question is, if I give you a set of angles that say my wrist is at this angle, my elbow is at this angle, my shoulder is at this angle, could you find me the final position of my fingertips? Right? What is the final position of my gripping tool? Right? My arms, my fingers. Where is it going to be? So it's a very important question, right? When we operate robotic arms, we need to know, like, is my hand able to reach at this point, or for what configurations? Where is my hand? Where is my hand right now, as in XYZ space in the world? So it's a question, and that is what we're trying to solve. And we solve it using one of the very, ancient, oldest concepts in mathematics. So that is using forward kinematics. Okay, this is what forward kinematics is. Forward kinematics is questioning, right? If I give you some configuration of the joint variables, could you finally give me the end effector's position? So that is the question. Do you guys understand the question? Yes, no? All right, so that is the question. All right, cool. So that is the question. And this is answered by forward kinematics. Okay. And you will see why it is called forward kinematics. All right, moving ahead. So we know it is forward kinematics, and what is forward kinematics. So as I said, we will solve this question using trigonometry, and we'll see what it is. So by forward kinematics, what we mean is a way to transform from the robot space system to the world space system. What is robot space system? What is world space system? See, a robot space system has in this case. So take a look at this, right? It has two variables. So this is a 2 degrees of freedom robotic arm. This, I guess you have seen a lot by now. So in this arm, there are two things that describe this, right? If I ask you what configuration is my robot in, then all you have to do is give me these two angle values. Once you give these angle values, oh, I know this is in this position. So this Q1 and Q2 are our robot space system, right? Like in XY is in our Cartesian system. Q1 and Q2 are the robot space system variables. So joint variables are part of robot space systems. Okay. So what we are trying is can we convert from Q1, Q2 to XY? The world space system is essentially Cartesian world, right? That consists of XY. In this case, XY. It's a planar robot. So in this case, it's an XY. So my question is, if I give a Q1 and Q2, right? If I tell you my robot is in Q1 and Q2, can you figure out the position of this in XY in world space? So this is actually transforming. So this is in technical terms, this is the technical definition, right? That you transform from Q1, Q2 to XY of the end effector. That is what we are trying to achieve. That is our goal, to get this position of the end effector. So yes. And okay, so this is the 2-hour robotic arm, and we'll see how it works on this. Okay, this is a very simple case. Robots can get complicated, but we'll look at the simple case and try to understand the principles behind it, and then you can apply it to any other. So right, So it's a very ancient thing. We use trigonometry, but it's still relevant today. Okay. So this is the figure. This is a diagram showing my robot. This is the first link, right? The length of this is L1, and this is my second link. This is L2, and this final thing that you see over here is the end effector. All right. So this is basic trigonometry. So if you have an angle subtending to the horizontal, right, then the projection to the horizontal is basically the length times the cosine. So it scales down by the cosine of the angle. And when you project it towards the vertical side, it scales down by the sine of that angle. So this is a very common thing. So to get the final xy position, we'll add up the parts of the lengths. So in this case, if you project this down, you will get the first length scaled down by cosine of the angle. And when you project this one down, essentially this is at θ1 plus θ2, right? So all the angles that we describe for this link is relative to this link. So you can see there's a line that is extended from this link. And so whatever we describe for this link is always relative. So when we just look at the horizontal, the total angle is always θ1 plus θ2. And so when you project it horizontally, you'll get the same result, except this time there is θ1 plus θ2. And when you project it vertically, you'll get the same result, except this is L2, and then it is θ1 plus θ2. Right? So basic high school trigonometry. And so you can see that the final x position, right, the final horizontal distance that you get is the sum of the parts, right? So it's L1 cos θ1 plus L2 cosine θ1 plus θ2. Very straightforward. The same thing to the final y position. It's the sines L1 sin θ1 plus L2 sin θ1 plus θ2. So it's the vertical projection, sum of the vertical projections of each link, right? That is it. So pretty straightforward. All right. So is that it? So well, yeah, right. So that's it. But I have to confess, right, something that in higher dimensional robots, like this is a very simple case. So for something much more complicated, we use something different things, right? We use matrices, we use rotation matrices, we use something called as it's called a Dennevit-Hartenberg procedure, right? So but then it is a complicated formulation, but it applies to any robot in general, right? So, but this is essentially out of the scope of this course, right? We just want to lay the fundamentals, the foundations of this, and the basic principles are the same. The math that works behind those things, the matrices and rotation matrices, are the same as this, but those are just a neater way to represent any general robot. So we'll stick with basic trigonometry for now, and can provide you materials and links if you want to, dive deeper and to see how those things are done. So we'll stick with basic things now. Okay. All right. Now let's see if we can try to code this up. Okay. We see how can we make use of this in simulation. All right. So at the end of the day, that is what we want to know. Right. So this is my code. Are you guys able to see it? Should I increase the font size? Or is it okay for you guys? Yes, no? Visible. It's good? Good. Okay, good. It's okay, good. Cool. All right. So this is the, the default imports. Whenever you're working with any PyBullet projects, you most of the times need these imports, right? So you will import all of these things right away. So these are just basic imports. This is the file, and this is the URDF file that I'm going to use. And whenever you specify like this, a relative path, remember that you have to have this file in your local directory, in your working directory. So if you can see, this is my working directory over here, and I have this URDF in the same place. So I can just refer to this as simply this, or otherwise, if it is not in your working directory, you have to specify the full path, right? The entire path of the file. So just to keep things easy, I'm just you can just put it in your same directory and it will work out. All right, so we connect it to the GUI, right? And we load the plane and we load our robot. So in this case, I'll load my robot at 0, 0, 0 at 0, 0, 0 orientation. Okay. Now I've created a constraint, right? So this thing, you have heard about this, just Is that a question? Import OS is for this thing. You have to join the path. So OS is a library. It's an inbuilt library in Python. It's used to manipulate your operating system basically. So you can get your directories, you can open folders, you can get what folders are in a particular files. You can do a lot of stuff with the OS, right? OS is essentially a module to work with directories and files and folders within your system. Okay, so what I've done is, okay, cool. So you can learn a lot about this. It's very important when you learn Python. OS is very important. If you do file handling, if you want to do some works on Excel and all of the other things, so you will have to use OS. So it's a very important module. You can look it up. It's a very interesting module. So we use time, we use math. Obviously, you should guess why we use math over here. So, okay, so I've created a constraint over here, and this constraint, all I'm doing is I'm just fixing the robot in place. All right. So, okay, I have a question. Why do you need to import the whole module and not the certain function you need? Yeah, well, I could, but then sometimes you don't know what you need, right? Sometimes you're just figuring out the things as you go and code. So I just imported the whole thing. So you can just, it's just to make this. This is not the most efficient code, right? The idea is not to make the most efficient code, it's just to make things understandable, right? So yeah, when you code for on your own, you can just specify the specific functions that you're going to use. So just for simplicity's sake, I've just imported the entire module. Just no big issues. So okay, back to constraint. We have created a constraint of my robot's base link. Okay, of my robot's base link to when we specify child body as -1, then we don't refer to a body, we refer to the Cartesian coordinates, right? So I refer to this as -1 because I want to fix it at origin. I can just show you what happens if I don't fix this, right? I'll just comment this out, and so you can see it just flies off the screen, right? I don't want that to happen. So it just flies off, and I'm just trying to fix it in place. So if I remove this, you can see now it just remains in place, right? So it's just fixed in place. That is all I'm doing. I'm just fixing the robot's base into the 0, 0, 0. Okay, at the origin, I'm fixing that. There's nothing much important there. So okay, so we have L1 and L2. So in my robot URDF, the lengths of L1 and L2 are 1 and 1. Okay, if in case you're using your own URDF, update the length. Okay, so if you're using your own URDF, when you design, you can control your lengths, right? So update these lengths respectively, correspondingly. Okay, so this is the primary function that we are interested in. Okay, so again, I want to remind what the question was, right? So the question was, given some angles of the robot, can you give me the XYZ position? So similarly, that is what forward kinematics as a function does. It takes two angles, right? It takes two angles and spits out Y and Z. In Y and Z, I mean, our equations were in X and Z. I mean, sorry, X and Y, right? But I can show you guys one more time. My robot is actually working in YZ. It's not in XY plane, it's in YZ plane. So this Z is the horizontal and Z is the vertical and Y is the horizontal. Okay. So this red is the X, this green is Y, and there's a blue axis. You can't see it right now. That is Z. So I'm working in YZ space. So that is why I'm using YZ coordinates. All the equations remain same. You can verify that. Okay. All the equations, everything that I'm going to be discussed later, everything remains same. Except I just use Y and Z instead of X and Y. So I've calculated using the math module, right? You can use the math module to find the cosines and the sines, and you figure out what the Y is, you figure out what the Z is, and I'm just printing out, right? Position of end effector, and I'm just printing out. This is called string formatting, by the way, right? So you print out Y and Z. That is what this function does. So we'll see if it does what we want it to do. So for that, I have, okay, questions. Sorry for the rush. Okay. Okay, so we have these angles all right, and we specify the angles, right? So I said we can specify angles. So in this case, I've specified 90 degrees and minus 90 degrees. So you can see that the robot is finally in this position, and from the simulation itself, you can figure out it's at 1, 1, right? In YZ space, it's at 1, 1. And you can see over here also, it is 1, 1. The position of end effector also is displayed as 1, 1. And you can similarly you can change this, of course, right? You can play around with this when you, I'll give the code in the GitHub, so you can play around with it. And if I actually set it to 0, 0, you'll see that now lies flat, right? From the simulation, you can figure out it's at 2, 0, right? And that's what it gives. 2, 0. It's, I can just show you guys one more time. So it's at 2, 0 itself. Okay, and you can see the position is spread out as 2, 0. So this function works. Okay, very great, good. So that's what we expected, and that's what we get. What this is doing, I'll just quickly go over this. This is how are we setting the angles? We're setting using the set joint motor control. This is also something that you guys have learned, right? I'm using an infinite loop to step the simulation. Inside the simulation, what I'm doing is I'm just setting the robot's first link to the first angle using position control, the robot's second link to second angle using position control. That's all I'm doing. Okay, so I'm setting these angles on the robot just to see it on the simulation, and then I'm calculating what the XY is through this function. Okay, so does that make sense? Is everything cool? Any doubts in this code? Yes, no, somewhat understood. Yeah, force, right? It's just an arbitrary force, right? I mean, you can just reduce it to any value. It doesn't really matter, because we have to give a force to like, if you have to, you know, make the robot stay at an angle, you have to give continuously a force, right? So if you want to hold your hand at this position, your muscles are continuously applying a force to keep your hand at this position. So we're just specifying some force. It's an arbitrary force. You can give any value you want, and it will fix. It's fixing the robot in place, actually. All right, cool. Okay, so that's the function, and you can play around with it. All right, I'll give it in the, yeah, the value doesn't matter. It will be slower, right? So if I'll just give a slower value, and it will just slowly lift off. You can see if I just give. So if I've given a lower value, you can see that, see, there's some oscillations and stuff. That's why, that is because of the reduced force. So if I give a very high value of force, it will instantaneously, you know, pop back into position. So that's what the force does. You can arbitrarily give any value. Finally, eventually it will find its position. So it doesn't matter really. Okay, cool. Okay, so that is done. Okay, forward kinematics is done. We've answered our question. So if you give me some angles, I'll give you an XY. So that question is answered. We're done and dusted there. Okay. So I'll again just go to full screen. All right. So this is my second question now. Okay. So the second question is, given the position coordinates of the end effector, what are my joint variables? Okay. Essentially, it's the reverse of the question. Okay. So if I give you the final configuration, so going back to our arm analogy, if I hold my arm in one configuration where my fingertips is, you know, at some position which I know, then what should those angles be, right? What should my wrist angle be? What should my elbow angle be? What should my shoulder angle be? So that is what this is what we're trying to question over here, right? So what is the position? If the position of the end effector is known, what are the angles that we need to give, so the final configuration of the robot will match with the position coordinates of the end effector, right? Does that make sense? Is the question clear? It's the reverse of the question, right? It's the reverse of the first question. Yes. Okay, cool. Okay. So this is a rather complicated question. Okay, sometimes when things don't go if things go very easy in the forward way, it's not necessary that it also follows the same in the reverse, right? It's not really easy to go backward sometimes. So for example, you can just try reciting ABCD in reverse, right? It's easy in one way, but it's hard in the other. But that does not mean you can't do it, right? It's a matter of experience. So right. So it's a rather complicated question, but it's a very important question. Okay. Because so could you think why it's a more important question than the first one? Right. So if I give you some idea, right, it's because most of the times we know, right, where we want to go. So when we're planning our trajectories, we know where we want to go we know where we want to move our arm. So if there's an apple on the desk, okay, assume there's an apple on the desk and I have a robot arm. I wanted to pick the apple. So I know the apple's coordinate. It is on the desk. I have some X and Y and Z values. Essentially, what I need my robot to do is figure out the angles on its own so that it can reach the apple, right? So this is what usually we apply in robotics. Sorry, let me just go through the questions. There can be multiple config. Exactly. And this is why it's a complicated question. Because sometimes you can have no solutions. Sometimes you can have one solution. Sometimes you can have two solutions. Sometimes you have multiple solutions. So really, it's a very complicated question. So sometimes it's right. There are multiple configurations. Yes. And even if there are multiple configurations, we'll get all of them using inverse kinematics. Okay, we'll get all of them. We'll choose which one is more efficient or which is the one that we are using. So that we'll choose. So we can choose from it. So there are also occasions where you can't get. So if the robot is trying to reach somewhere that is out of its scope, right, out of its reach, then inverse kinematics will not give you a solution. That is also a possibility. So that is why it's a complicated question, but it's a very important question. This is what we're using most of the time. Okay, and we needed to understand forward way to better understand the reverse way to have a better understanding of inverse kinematics. That is why we went over forward kinematics just briefly. Okay, so let's move. So this figure will describes the idea, right, in a much better way. So what this is telling is the forward kinematics goes from joint angles to position, while inverse kinematics does the reverse thing. If you give it some position, it will give you the joint angles for the robot to have a final configuration that you want it to have. Okay. So if you can see over here, it says that it is a transformation from the world space system to the robot space system. Essentially the reverse of the first thing. Okay, cool. So we'll briefly go over how we'll do it. Okay. And this is complicated, as I said, but we'll do it. Okay, we'll figure it out. So let's find out how we can do it. So we'll go back to the same example, right, that we were working on. We'll go back to the same example. And so I have a diagram over here that is representing my situation over here. Okay. So you have X and Y axis. You have my robot arm. Lengths are A1 and A2. Angles are Q1 and Q2. And I've specified an angle alpha and R. So I just want to remind you that what we're trying to get this time is we know this XY. What we're trying to figure out is Q1 and Q2. Okay. Now to get to Q1 and Q2, right, we need to walk through some other angles, some other triangles, and we need to do a bit of work before we get to Q1 and Q2. So let's see what are those. So yes. So I've defined an R over here, right? This is the distance from origin. So in Cartesian coordinate space, any point distance from origin is x square root of x square plus y square. And if I just square it, it is x square plus y square. And this comes from the cosine rule, right? So the cosine rule says that if you can see this highlighted triangle over here, in this triangle, the R square is equal to the sum of the opposite side square, that is A1 square, A2 square, minus 2 times the product of these two sides, the opposite sides, A1 and A2, times the cosine of the angle that is subtending between them. That I have defined here to be alpha, right? So it R square is A1 square, A2 square minus 2A1, A2 cos alpha. That is R square. So we now have two equations for the same R square. So we'll equate it, right? So we have cos alpha equal to A1 square, A2 square minus R square, and we substitute this R square from the first equation. So we get this alpha. Now, why alpha is important over here is because if you observe, this is a straight line, right? And these two angles must add up to 180 degrees. That is pi, right? So you can see that Q2 must be pi minus alpha because this is straight line geometry, right? So you take the cosines at both sides. So you'll get cos Q2 is minus cosine of alpha. And so you know cos alpha, very convenient. So just replace that and you will get the cosine of Q2. And that's half of the job done, right? Because we know the cosine of Q2. Then all we need to do is take the inverse cosine, right? This will give you a value because all these things are known. X is known, Y is known, A1 is known, A2 is known, everything is known over here. Just take the cosine inverse of whatever the value comes out, you will get the Q2. Okay, half of the job is done. Okay. Again, now finding the, okay, now again, moving on. So that's Q2. Now I've chosen a different triangle. All right, this is a different triangle. And I've chosen a different angle beta over here. Okay. And these are some of the lengths that we would need. So you can see this is Q2. And if you project this length, it will be A2 cosine of Q2. If you project it vertically, it will be A2 sine Q2. And this entire length, okay, the entire base of the triangle will be A1, which is the length of the original first link, and then the projected length of the second link, which is A2 cosine Q2. So the entire length will be A1 plus A2 cosine Q2, and this will be A2 sine Q2. So essentially, we're trying to find out tan of beta, right? And that is it. So you can see that tan of beta comes out to be the opposite by adjacent, that is A2 sine Q2 by A1 plus A2, and we just taken the tan inverse of it, inverse tan of it, right? So simple trigonometry. Okay, moving on. Now this time I've taken another triangle. Okay, this will eventually end, I assure you. So I've taken another triangle this time, and I've specified another angle gamma over here. Okay. So you can note that gamma is tan inverse of y by x. So because I've considered this entire triangle that goes to this xy position, again is opposite by adjacent. Opposite is y, adjacent is x. So you get tan inverse y by x. Now again, why this gamma and beta? Because again, if you observe, if the q1 and beta add up to gamma, right? Q1 plus beta is gamma. So what q1 essentially is gamma minus beta. So that is convenient because we know gamma, we know beta, right? We know gamma from here, we know beta from the previous slide. Again, very convenient. So substituting back into those, so we know q1, tan inverse y by x minus tan inverse A2 sin q2, whatever that expression was. So that is great. That's all that we need, right? So if I give you an xy, you can give me q2, which is cosine inverse x square plus y square minus a1 square A2 square. All of things are known. You can also give me q1, tan inverse y by x minus tan. These all these values are also known. So note two things over here. You have to calculate q2 first. Why you have to calculate q2 first? That's a question. Okay, so you have to find q2 first because you are using essentially q2 in the second equation, right? So the order is important over here. You have to calculate q2 and then substitute in q1. Again, why did we get multiple configurations? Is because this cosine inverse can give you different signs. It could either be positive, it could be negative, depending upon the values. It could be plus or minus. So the plus or minus gives you the different configurations of the robot, right? Okay. Okay, moving on. So we've done the job over here. All right. So yeah, we're done with it because we achieved our goal, right? We got angles. So once you do with it, okay, once you get the stuff, okay, get the mathematics out of the way, these are all the cool things that you can do with it. Okay, once you figure out like this angles for any position, then you can essentially maneuver your robot in any way you want, right? If you specify any trajectory that contains some xy positions, your robot can easily navigate because it knows what the angle should be to navigate through those positions. So the robot can do crazy things like this. Okay, these are very simple things, but you can also do very complicated things as well because now it has become easy. The robot knows what the angle should be. So we'll attempt to do one of this. Okay, we'll use this. We'll use to try the circular trajectory because our robot is a planar robot. This is a XYZ robot. Okay, you can see it. It can also rotate along the Z-axis. Ours is just a planar robot. So we'll attempt to do this. Okay, so let's code it. So so this is my code. These are the basic imports, same as that in the previous code. This is again the same thing. Okay, and I'm fixing the robot in the place. Everything is same as before, except the lengths are also the same as before, except I've used inverse kinematics as a function. Okay, so when I use inverse kinematics, what this does is I'm essentially giving it a target, right? I'll give it a target in terms of y and z, and once I give it a target, it will spit out an angle. Okay, so it gives me an angle 1, angle 2. What's the question? Yeah, Fourier transform is yes, you can also do that in Fourier transforms. But we'll use a simpler representation over it. We don't need to get to Fourier transforms. But yes, any arbitrary trajectory can be represented as sines and cosines. So you can do using Fourier transforms. That is also very much possible. But in here, we don't really need Fourier transforms because we get a very finite expression, right? That is an infinite expression. We get a very finite expression. Okay, so we don't really need to do it. Okay, so same equation, except I've just used it y and z. Okay, and the angles will get some angles. Okay, you can verify those equations, and this is a circle that we'll try to implement. Okay, so I've chosen this specific circle because you know, my robot has some limitations to where it can. So this is one of the circles that fit inside the task space of my robot. So I'm just going to use this. And I've used theta. Why? Because I'm actually using polar to coordinate to polar transformations. So this is a very easy way of representing circular motion and everything, right? Essentially what you do is you convert this equation into polar coordinate forms, right? And so I've reduced this equation from 2 variables of y and z to just a single equation of theta. So just for the ease of it, I've just reduced it to a single variable theta. And now I can just increment theta, right? So once I do it, I have an angle using inverse kinematics. Every time, this is my trajectory equation. Okay, this is the equation of my trajectory. Every time this loop executes, I will get a new y and z point that my robot has to follow. Now, how it will follow is given by this inverse kinematics. If I provide those coordinates, it will give me some angles. Now I can specify the angles to the set joint motor control. So it will command the robot to go into that angle. Okay, and I've incremented theta in every loop so that it gives me new points as we go. Okay, so let's try to run it over here. Let's see. And you can see it gives, oh, let me slow it down a little bit. So if I increment the theta slowly, the thing will move slowly. So you can see that it is executing a circle. Okay. So it's doing, it's making a circle, but I don't know if you trust me or if the visualization is not proper. So let me do something over here. What I will do is I'll specify and something. So I'm trying to, so in PyBullet, what you can do is you can't create trajectories or you can't actually create curves, but you can create lines. Okay, you can draw lines in PyBullet. And what I'm attempting to do is basically a circle is just infinite lines, right? So if I draw lines between the 2 points of the circles and I go through the entire circle, I should eventually get a circle. So that's what I'm trying to do. So this is my starting position. Okay, you can see that this values equate, okay, satisfy the equation. Now what I'm going to do is I'm actually going to use this function. It's called p dot add user debug line. Okay, this is a function that we use to draw lines. And what I'm going to do is from the old point, that is from the, if my while loop is running, the points from the previous loop to the point in the new loop, this will draw a straight line between those 2 points. And I can also specify a color. So you have to give it an RGB. So I'm using a red color. So I'll give RGBS. R is 1, green and blue is 0. So it will essentially draw out a red line. So it will draw a line between old points and the new points. Okay. So, but I also have to update the old points, right? Whenever a new points come in, I have to store that to use that in the next loop. So I'll just specify that. Okay. So I do that. And now it should trace out. Okay. Should. Hope so. Okay, it is. Let me just increase the speed a little bit. So now I can properly see that it's tracing out and it's following the circle. It's following the trajectory. So that is what we're doing. Okay. When you guys do it, implement it on your own. You can try a lot of trajectories, not circle. You can do sines, cosines, any sort of XY that is possible for the robot to do. You can give the robot and you can do some fancy things with it. Okay. Try it on your own, play around with it. Okay. So we'll stop it for now. Yeah, if the position is out of the robot task space, it will give you a domain error. Okay. If this cosine inverse and tan inverse has some domains, like it can only take some values, right? So if the y and z coordinates get out of the range, it will give you a domain error. So eventually the program won't work. So it will give you a domain errors. Is that good? Okay. If the robot is out of the task space, then how do you know the robot task space? That is just inspection, right? So, I mean, if you look at my robot, two lengths are L1 is 1, L2 is 1. Okay, so if my robot is standing upright, it can essentially trace out a circle, a semicircle in my a circle. Okay, so it's a planar robot, right? And I can rotate it. So that means it traces out a circle of a radius 2. Okay, my first link is L1. I'll just show you in my forward kinematics. Okay, you can see that finally it's good. This is the maximum it can achieve, right? If I set all my angles to 0 and everything, this is the maximum my arm can reach, 0,2, right? So essentially, if I rotate this arm, what it will do is it will trace out a very large circle of that radius 2. Because my lengths are in that way. This length is 1, this length is 1. So if I trace out the maximum my arm can reach is a circle of radius 2. So I have to find a trajectory that is inside this circle, okay, inside the task space. So task space for my robot is a circle of radius 2. Okay. And so for other robots, it will be given by its properties. Okay. It will be given by its length, joint lengths, how many number of joints are there. You can figure out using forward kinematics. You can figure out what are the maximum positions that you can achieve. That is how you figure out the task space. Okay, is that cool? Great. So okay, all this code makes sense, right? Everything is very much done. Okay. So we'll move ahead. So yes, so this is a very I know some of you might have annoyed by this mathematics, triangles, angles, and all alpha, beta, gamma, and everything. So this was a very simple case. Okay. And imagine what will happen if I go to higher dimensional robots, like if you have multiple joints, if you have X, Y, and Z, and you have various joints, various links, and all these things make things very complicated. Okay, the math becomes so much complicated that is almost impossible to derive the equations from scratch. Or sometimes you don't want to take the time to doing it. Why? Because PyBullet understands your concern. Okay, and PyBullet has an inbuilt functionality to calculate the inverse kinematics for you. Okay, so that makes our life very easy. So for complicated robots, you can use this, okay? Or even the easier robots, you can use this because it will calculate it for you. Okay, so that's great. So we'll see how we can incorporate this. So this is the function. It's called calculate inverse kinematics. I've taken this straight from the documentation. Okay. So this is Pybolate inverse kinematic solver, and the function is calculate inverse kinematics. It takes a bunch of arguments, but only 3 are required. Okay. You have to specify the body. You have to specify the end effectors link, right? What is the link? Okay. So the which link is the end effector on? So, and then you have to specify the target position, which will be XYZ. And then you can also specify orientations, limits. These upper limits and lower limits is what you said, some of you said that there are various configurations. So we can limit the robot to choose from only within this configuration, choose that. So we can specify the limits of the inverse kinematics and all of that. You can go through the documentation for additional things, but right now we just need these 3 or maybe 4 things. So okay, let's try to implement this into our code. Okay. So okay. So what I'm going to do is I'm just going to define a variable over here. It's called use custom. Okay. And I'm just going to define it as false. So if use custom is like our custom made function, right? If it is false, if it is true, then it will use our custom made functions. If it is false, then we will calculate the angles using inbuilt. Okay. That is p dot calculate inverse kinematics. So in p dot calculate inverse kinematics, I have to specify the robot. Okay. I have to specify the link of the end effector. In my case, my first link is the first link L1, second link is L2, and at the end of the link, there's a small tiny thing on the end of my robot. So that is the third link. So its index will be 2. And then the target position, right? So target position is Y new and Z new. Okay. So I've set the custom to false now. That means it is going to use the inbuilt calculate inverse kinematics. I specified all the arguments over here, and let's see what it does. Okay, let's see if it works. So now you can see that it's actually going beneath and drawing it. Okay. So this is again the thing that this guy said, that there are multiple configurations of a robot that can achieve the points. So previously we were doing from the top, now it's doing from the bottom, right? And so what I can do is I can specify a rotation. Okay, so if I go back to the documentation, you can see that there's a target orientation. You can specify the target orientation. So this should be the orientation over here actually. So the rotation should be 0 pi. Okay, I'm rotating about the y-axis just to invert the whole thing. Okay, and I can just specify this rotation. So now it will calculate inverse kinematics based on this particular thing that I want, particular orientation that I want. And so now you can see it flips up, it flips back up. Okay. So this is how you can get across those multiple configurations. You will choose what configuration do you want. You will limit the robot to actually tell you what configurations do you want. And this is how you get around that. So inverse kinematics will give you multiple configurations. Sometimes no configurations. You will have to choose accordingly. Okay, is that cool? Is everything clear over here? Shall I continue? Yes, no. Something is missing. Okay. Cool. All right. So that is it, to be honest. We're done here. All right. So just for a quick recap, you've learned what is kinematics. How do you use it? How kinematics applies to robots? How do we plan a trajectory? How do we plan a motion? What is forward kinematics? What is inverse kinematics? Why? What are the questions that these two things ask? All right, and how they give the answers. And so we looked at the very basic example of how they solve the thing. Okay, so this is mainly used for trajectory plannings and motion plannings. If you want to move a robot in a particular way, you will essentially you're going to use this, okay, inverse kinematics and forward kinematics. It's a very important part of the robotics thing. Okay, so I hope you guys understood. Thanks for joining in. All right, I want you guys to scan this QR code, okay, and this it should hopefully give you to give a link to the feedback form, okay, and just fill the feedback form. Tell us what you like. All right, so I hope you guys have understood things. Right, so is everything cool? All right, great. So I hope we can see you back tomorrow. Okay, tomorrow the things are going to be very exciting. Okay, all this day, I mean, there was a lot of theory and there was a lot of studies and all of things. Tomorrow we'll be actually executing things. Okay, we'll be actually executing some fun simulations and actually trying to solve some problems, trying to solve some real world problems. So it will come. So these things will come in handy there. Okay, and okay, join that tomorrow for that things. Okay, great, and don't forget to fill the form. Have a good night. See you. Okay, great.
Yeah, Vamsi, I think you can stop the recording.